Hello, students. First three sections, we're talking about congruent shapes, shapes that are exactly the same. And that means every angle that is corresponding matches up perfectly. Now, for similar shapes, the angles will still have to be exactly the same. Corresponding angles have to be congruent. But now the sides do not have to be the same. They can be scaled up. Now, just to understand how this connection works then. Similar means they have to be in proportion. So if something is congruent, then by definition, they will be similar. It's just that the ratio will be 1. Okay. Otherwise, if they are not, if the ratio is not 1, then they will be similar but not congruent in terms of the shapes. All right, so we do have this thing called a scale factor. Remember, scale factors can be also written down in such a way that it makes it so very big things look very small. Okay, so if you had the model where the model was 500 feet tall, but you were compressing it down into a model that was 1 foot tall, then you would have a ratio of 500 to 1. You could also have a ratio of something like 1 to 10. So 1 inch in reality is 10 inches here. And so this, again, if you're thinking about things that are very, very small, like cells or bacteria or viruses, then we have a scale factor that indicates that what we're looking at is extremely blown up. Now, if we see this as a ratio, and so let's just say we have big over small, something like that, the ratio has got to be bigger than 1 because your big component is bigger than the small component. And so when you think about things like on a photocopier being blown up, then your ratio will be something like 1.25, which is another way of saying 125% of the original picture, or a 25% increase. And just like we saw back in the section on fractions and decimals, so back in chapter 6, we got a chance to see we could go the other direction too. We could go, and I guess a little bit into 7 when we did percentages. But let's just say that we had a ratio of 0.80. Well, that's 80% of the shape, which is a 20% reduction. So if you look on a photocopier, sometimes it'll say, what percent reduction do you want? So if you put in 20% reduction, then it multiplies everything by 80%, by 0.8. And again, that's going to be the difference there. Okay. All right. Let's see here. Oops, there we go. Similar polygons. Again, doesn't have to be just triangles. Triangles have exactly 3. So triangles have very specific pieces. And let's take a look at those. We did review these in class, but we'll go over them again here. For triangles, side, 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 side angle, side, and the power of the angle, angle. Again, for a triangle, there's only 3 angles. So if you know 2 of them, you guarantee you know the third. So side, side, side similarity, side, similarity, and then angle, angle. Now notice that means I don't need angle, side, angle, and that's because one side cannot be proportionate. It can create a ratio, but a proportion requires 2 sets of ratios. So as an example, A over B, this is a ratio. C over D, this is a ratio. And when the 2 ratios are equal, that's when we have a proportion. Okay, so angle, side, angle, 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 side, side, angle, angle. Really, all of these turn into angle, angle. And I guess really angle, angle, angle should fit in here too, because that's the same. Once you know 2 angles are congruent, the triangles are similar. That's a pretty powerful tool. And so again, when you see shapes, look to see, do I have 2 triangles that match up with at least 2 angles? So here, angle A matches angle D, angle C matches angle F. I'm done. Those triangles are similar. Okay. Over here, a right angle and this. And then now again, this is sometimes, I'm not going to lie, this is where occasionally students do have trouble, because what they see is when you're looking, you see this triangle right here, the smaller one, but you have to use that same angle to draw the bigger triangle that's behind, and the bigger triangle is similar to the smaller triangle. Okay, keep that in mind. That happens a lot with parallel lines and figures that are created from parallel lines. All righty, let's see here. What else do we have here? Find a pair of similar triangles. Now, we've got to use all of the pieces that we've had to this point in time. So when you see shapes, they have to give you some clue. Here they say these bottom two lines are parallel. Hey, if they're parallel, corresponding angles are congruent. So this angle matches and that angle matches. Those are corresponding angles. Okay. Why? Because I've got two lines cut by a transversal. The first transversal was AC. The second transversal was CE. So those are congruent. And you didn't even need those both because you've got one angle up here that's going to be the same for all of them. So angle similarity. Here, let's check on the right-hand side. They both have a 90-degree angle. And oh, boom. They both share with the vertical angle congruent. So I got two angles. Done. So again, they can be pretty quick. I guess that's the thing with, because you pick up this angle similarity, two angles is all you need. So, and again, that happens often, especially when you make right angles. This is one I showed in class with the pond, or in my case, I was talking about the river situation. So very, very similar. Okay. All right. Let's take a look. This is going to be some like that are in the homework. So it says, show the triangles are similar, then solve for x, which is the missing piece. Now, one thing to notice here is, yes, you pick up angle, right angle, and then angle C is congruent by vertical angles. So we know the triangles are similar by AA. And one other piece that kind of tips me off there is they didn't give me enough sides. I'd need to be able to create proportions for these sides, and they didn't give me enough. They gave me this piece and that piece. Well, that's fantastic, but it's not enough to get a full proportion. Okay, so now that I know they are similar, I would say, aha, so 5 is to 8. That's AB is to DE as, and then I'm going to put this down here, DC and BC. So BC is right over here and DC is right over there. Now DC is X. Okay. And up here, I don't know what I would call BC. I don't know the number for that, but I'm going to just say it's 12 minus X. So that's what I'll put on top. And then we can use our proportional reasoning to rewrite this as 5x equals 8 times 12 minus x. We can write it that way. I'll show a second way because I like the second way a little bit better personally. But we'll kind of see if maybe you'll like it better too. But we'll see. So this one involves me. Now I have to use the distributive property. And so I have to distribute this. And so let's see what we end up with here. 5x equals 96 minus 8x. Then I bring the 8x to the other side. So I get 13x equals 96 and x equals 96 thirteenths. Okay. Second way of doing this is you can divide the x into both sides. So you have 5 over 8 equals 12 over x minus 1 because x divided by x is 1. So then add 1 to the other side. And if you take a look, if I add 1 to the other side, I'm going to choose a fancy form of 1 because the other side has a fraction of 8. So I'm going to write this as 8 over 8 and add 8 over 8 to both sides. And now what I've got is 13 over 8 equals 12 over x. Okay. And now using my proportional pieces, I can rewrite this by flipping it over. 8 over 13 equals x over 12. And then I just multiply by 12 and x is equal to 96 over 13. So I get the same result, but I don't have to do quite as much algebra, at least in my mind. I don't have to do distributive property. I don't have to combine unlike terms. I just simplify. And my simplification at first is to basically create a situation where there's only one x value. And that is pretty quick. Okay, next one says, explain why these are similar. So take a look. They gave me one angle, but they gave me no other angles. That tells me angle is out. I need to have some sides here. So let's take what they've given me. I see a 26 and a 24. So I'm going to write that out. 26 is to 24 as, I don't know, 39 is to 36. This is a question mark. Are these the same? So now I have to do a little bit of work. You know what I'm going to do is I'm going to simplify down. You could multiply to check using the properties from chapter 6, but I think that would require me to probably have a calculator. And instead, I'm just going to flop this one by 2. So that gives me 13 over 12, and flop this one by 3, and that gives me 13 over 12. And those are equal. So therefore, this is side angle side, because the sides, 2 pairs of sides, are proportional, and there's an angle between them. So again, a lot of good stuff in this section. Really kind of cool stuff when you start talking about how we can make additional proportions. And this is one of the nice theorems that if a line parallel to one of the sides intersects the other side, then it divides those into proportional segments. And that means the line could be parallel anywhere. So I could have drawn a line down here, and as long as it's parallel, then it would create proportional segments. And let's see here. In this figure, if this is parallel, then AB is to DC as AC is to CE. Okay. It doesn't tell you what the proportion is. Let's be careful there. It doesn't tell you what the proportion is, but it does tell you that they are proportionate. Later on, we'll see a lot of things in math come when you connect midpoints. If you connect midpoints, the reason this is so beautiful is then the side length, short piece to long piece, is always going to be 1 to 2. And that means this portion right here compared to the long side at the bottom has to be in the same ratio of 1 to 2. So that, again, pretty cool. You can create multiples. This is this is how we can create a line segment that gets cut by many pieces. And so that's kind of a cool one. And let's see here. So here we are. Let's say it says, given that these are parallel, if they are parallel, and just remember, if they are parallel, then corresponding angles are congruent. If corresponding angles are congruent, then the triangles are similar, right? If they're similar, the sides have to be proportionate, and we get a whole bunch of beautiful pieces here. Now, what that means, though, and this is what's great, is it means I don't have to create AE is to AB. Now, there's nothing wrong with that, but it makes it longer. So instead of me having to do 18 to 30, I can do 18 to 12 is X over 8. Okay. Now, floff a little bit. You know how much I love floffing. I know. So let's see here, divide by 2. This gives me, actually, I guess I could cut a 6 out of this, right? Cut a 6 out. That gives me 2 over 3 equals X over 8. And then you might just be able to do this one in your head by floffing. I can see a factor of 4 and a factor of 4. So X equals 12. And I am done. Again, you could do it with cross products. You could multiply here, and then go through and solve for X. There's nothing wrong with that either. Sometimes I just like to, if I can simplify this, why wouldn't I make it smaller instead of jumping over here and kind of having additional large numbers? Totally up to you as you go through these problems, though. Okay. If a line divides 2 sides into proportional segments, then the line is parallel. So this is kind of a back and forth. This is a two-way street. You could have made this if and only if. If the line is parallel, then it breaks it into proportional segments. If it breaks it into proportional segments, then the line is parallel. And so we get this kind of really nice connection between the two. And then it says if parallel lines cut off congruent segments on one transversal, they cut off congruent segments on any transversal. And so this is how we use it, is we use it to create a line segment that can be cut into as many pieces as we want. Let me open up GeoGebra here and demonstrate really quickly, because I think this is such a cool approach. And if you're interested, ask me in class. If you're interested, we can show you how you can do it with just a sheet of lined paper. And I think I posted, there's actually a guy online who was doing this with Maybe I'll show that at the end. There was a video of somebody doing this basically on a construction site and saying, hey, I'm trying to find exactly, I have a piece of wood. I'm trying to find the middle of it. And he didn't want to do a lot of math. And so he showed that this technique could be like, yeah, I don't need to use a lot of math. All right, here we go. I'm going to make a segment. Here's my segment. Now, take a line and take it up in any direction you want. And then create, using your compass, mark off some distance, whatever distance you want. And I'm going to go ahead and translate by a vector. Select the object, point D, and then the vector. There we go. Okay. So what I'm doing is that basically I'm saying, take your compass and just kind of tick it off. Use it to make a new point, then make another point, make another point. You do this as many times as you want. Right? So I've made 1, 2, 3, 4 pieces. Now, again, making 4 pieces as like a bisector, that's not bad because I can just cut it in half and then cut it in half again. There's 4 equal pieces. But if I had to make fifths or sixths or sevenths, that would be problematic. And so I could just, and if you were doing, let's see here, how could I do total, select segment, circle, or 2 points for a radius. There we go. So you basically take this and just keep moving your compass down to the next point. You see what I'm doing? Keep moving my compass down to the next point. Every time I find one of these, I create a new point. Okay. Now I will hide those, the circles here, because again, if I was doing this, I probably wouldn't use a whole circle. I would just use an arc of a circle. Okay, so now I have, look at my new line segment. I have 1, 2, 3, 4, 5 segments. And down here, but my goal is to make AB. I want to cut AB into 5 pieces. And you're like, you're cutting the wrong one, Scott. You're doing it wrong. No, the issue is I don't know. Remember, this is a compass and a straight edge. I can't guarantee how big is AB, and then where would be 1/5 of each of those parts. By creating it the way I did, I'm able to construct a line and then use one of my famous parallel line pieces to create parallel lines that go through the next point. So what I've done, can you see it there? I have created these parallel lines. Parallel lines, when they are parallel inside of a triangle, create proportional segments. So the segments will be in the same proportion. So since each one of the pieces on the top line is 1/5 of this total, then each of the pieces on AB would also be 1/5 of the total. And I could make points here. And if you wanted to, I mean, you can measure those. There is the measurement area. Select 2 points. So I'll pick A to F, and it says AF equals 2. Got it. I'll pick G to H, and it says GH equals 2. Well, that's impressive, right? BI, well, that equals 2. And I can even say AB, and AB is 10. Now you can see it's 10.1. That's only because of rounding. So AB is 10.1. Every one of the other pieces is exactly 1/5. Now here's what's great. I can grab B and I could pull B and say, what if B was bigger? Doesn't matter. Because of the way this is done, I can actually make this work no matter how big or what angle or what direction AB is located. So there you go. That's pretty quick. Yeah, and again, I think it'd be cool to show you how and why this is easier than some of the other methods, but let's take a look at the rest. Anyway, there you go. Let's see your mid segments. Like I said, this is one of the big ones. Mid segment, basically, I don't even know why it's a theorem, but it basically says if you take the midpoints and you connect them, you will have a 1:2 ratio. But again, it's because a midpoint is half of the length. So of course that's going to work. And let's see here. If a line bisects one side of a triangle is parallel to the second side, it bisects the third side. Therefore, it's a midsect. Whatever. I don't even know why this is a theorem. If it bisects one side of a triangle and parallel to another side, then it has to bisect the third side. Well, again, if it's parallel, then it has to create proportional segments, right? A proportional segment of 1 to 2 on one side means it's got to be 1 to 2 on the other. So anyway, that's clearly not one of the biggest pieces. However, as we expand this to be for quadrilaterals, we create really cool shapes. And I already made a video kind of about this. For what kind of quadrilateral will this be? A rhombus, MNPQ. And what kind of a quadrilateral is MNPQ? So what's great is if you use all the pieces that we've talked about today, and you really focus in on things like this set of triangles right up here on top, you can see you have a line connecting them. And because they are midpoints of the sides, you know you got the angle in the middle and proportionate. That means the lines are parallel. And if the lines are parallel, then we get some really cool stuff, because if lines are parallel, that means this piece right here is parallel to the one in the middle. Repeat that over here on the other side with this larger triangle, and you'll be able to show that the one in the middle is parallel to the one on the right. So at the end of this, I'll be able to say that MN is parallel to PQ. And now repeat the same argument, but just go the other direction. NP is going to be parallel to BD, which is going to be parallel to MQ by the transitive property. NP is parallel to MQ. So what kind of a quadrilateral? I can now demonstrate and guarantee that it has to be a parallelogram. That's pretty cool. And again, if you want it to be a rhombus on the inside, then we're going to need to have some of these diagonals. The diagonals are controlling the length of these sides. Remember, with the midpoint theorem, they're going to be half as long as the diagonal. So if you want this piece over here, this piece is going to be the same length as that one, guaranteed, because it's got to be half of BD. But if you'd like it to be exactly the same length as MN, then MN's doubling piece, which is AC, right? Then AC has to be the same as BD. That's what we need. So it's a rhombus if the diagonals are congruent. But again, just utilizing the pieces and the properties that we've had so far. I guess there's one more piece, one other center of a triangle. This is a really cool one. Hey, look, side. I gotta write that down because they have had some serious issues with their quality this term. Let's see here, page. Just craziness here. Page 787. First paragraph. You'd think they'd have a spell checker on something like this, right? I mean, you're paying enough for the book. All right, last piece is called the median. A triangle has 3 medians, and a median simply connects a line segment to its midpoint on the opposite side. That does not mean that it's an angle bisector. Okay, it might be an angle bisector. It doesn't guarantee that it is, and it certainly doesn't guarantee it's a perpendicular bisector. Only for certain triangles is that true. But what's great about this is that when you connect all of the medians, and really you, again, only need 2 of them, but the point that you find, this point right here in the middle, has a special name, and it's called the centroid. The centroid is the center of gravity. So if you are building things and you're trying to find out where is the center of gravity, that means where could I balance this shape on a single pin? You need to find that centroid. And so this is, with a triangle, this is how you could do it. There's a couple cool videos online of people doing it with shapes that are not triangles. And so they kind of hang it from one direction and draw a line, let a line hang down perfectly, like gravitationally pulling it straight down, and they snap that line like a chalk line on top of it. They turn the shape and repeat the process and do it again. And guess what? You can find where that center is, which is really pretty cool. All right, let's see here. This one is show the centroid of a triangle divides each median into segments with lengths in the ratio 1:2. Now, this is a pretty cool property. So these medians, what they're saying, and I think sometimes their language gets a little complicated, but this length here, this BG, if you compare it to MN, it will always be a 2-to-1 ratio. Okay, always. So basically the median kind of chops this thing up into 3 equal length segments. 2 of them make up the long part, 1 of them makes up the third part. And that's true for all of the medians. And again, if you want to kind of see that, you can over here. Let's just make a new, we'll make a new shape. Ooh, let me clear my drawings. Okay, so here's a quick triangle. And let's get midpoints. Midpoint, okay. And there's our midpoints. And then I'll create segments from a line to its midpoint opposite. And we can see they've already intersected. The third one is guaranteed to intersect at exactly the same point. And then we'll come down here and we'll just measure. What is this distance from B to G? Oh, it's 3.1. Got it. And from G to E is 1.5. Again, I could add a little bit more in terms of accuracy on the decimals, but basically I want you to see that no matter where I move these two, that the short side is always going to be half, if you will, of the long side, or the long side will always be double the short side. So again, GE is right here and BG is right there. And that's true for all of these. If you wanted to measure the others, you certainly could. Let's measure from A to G, and it says 5.4. Then G to F should be 2.7, and it is. So really cool properties here about triangles. And I think, yeah. Then they talk about how can I use these to determine how do I use similar triangles in the real world for something that's meaningful? And similar triangles can be used to kind of measure things. We talked in class about the shadow, measuring a tree or a building. And that's exactly what we can do here. And in this case, someone is holding a meter stick vertically and it casts a certain shadow. Awesome. If a meter stick casts 2.5-meter shadow and the tree casts a 40-meter shadow at exactly the same time of day, I could use that to create similar triangles because I have an angle and the sides have to be proportionate, but also that the angle of the sun coming in is going to create congruent angles here. Okay, so angle similarity, and you are off and running with your proportions. You will see some of those questions in the textbook. And oh, hey, that's it. All right. Well, let's see here. Miracosta. Let me jump over to Canvas, see if I can find that short video. Again, I love showing pieces where it's it can really show you how you could use math in a meaningful way outside of the classroom. So inside the classroom, anytime you have something, if you just have a sheet of lined paper, you can just adjust the lined paper, like hold one line on the other. I'll have to show you in class probably. Now hold one line on, and then you just kind of line it up so your line segment is right on one of your lines, and then keep your point holding on one side and bring your lined paper down and just kind of slowly bring it down. If you bring it down one line segment, 2 line segments, you can cut it right in half. 3 line segments, you cut it in thirds. 4 line segments, you cut it in quarters. So it's pretty cool. Let's see here. Did I post it in here? I can't remember if I did. I did. Maybe? Let's see. Maybe. Okay. So this is on a construction site. And he's going to try to find the center of a board. Okay. Let's see here. And all right, dude, give it to us.
We got 7 1/4. Who wants to do the math on that?
Who does?
Take your tape, rotate it till it lines up on the edge of a number you can split, right here. 8, half of that is 4. Got 3 5/8. 3 5/8. Quick tip for finding the center of bore.
So there you go.
We got
Now,
7
let's take a look at
1/4.
what
Who wants
else
to do the
could
math
have
on
been
that?
done
Take
if
your
you needed
tape.
to do more cuts. So what I want you to see is what he's doing. Again, he's not showing you all the math behind it because maybe he either doesn't know, doesn't care, or that's not the point. But when you draw this line right here, this line that he's creating matches up with this beautiful triangle. And so he's got a right triangle there. And so all he's going to do is he's going to create some parallel lines. In order to do that, he just has to know where to cut. So if he goes to the 4-inch mark on an 8-inch length, that's the midpoint, right? And so all he has to do is cut perpendicular to that, and he's done. He's got right in half perfectly. He can find the middle. He could also cut this into quarters if he wanted to by saying, wait, here's 8 inches on the side, cut every 2 inches, 4 inches, 6 inches, and there's 4 equal pieces. So again, very quick way to do it. And I really enjoy things like this, especially for boards that aren't perfectly 8 inches, 10 inches long. This just tip your tape measure up and you can cut something in half. Now, if you were trying to figure out where to make a cut for this and you weren't sure how to make it perpendicular, okay, simply move your tape measure up a little bit more, anchor it down, and repeat the process. Find another point at the 4 mark, tip it up until you get to 8. You now have 2 points at the 4 mark, and you can draw right between those. Pretty quick way to do it. All right. Anyway, I love this stuff. Obviously, hopefully you can see my energy, my excitement, and that you are enjoying it as well. I will hit a few videos on the homework and the MCs, and we'll see you back in class soon. All right, off you go.